Step-by-step exam solutions. OK Physics class, training you to excel. Subscribe to step-by-step exam solution. Like the video. Share the link with others. Click for alerts so that you receive the next presentation. Please drop your comment for a better service. OK Physics class. Present step to exam success. Step 1, pray. Step 2, plan. Step 3, prepare. Step 4, review. Step 5, perform. OK Physics class. Present step-by-step exam solution to radioactivity number 2. Radioactivity number 2. In this particular presentation, we're going to be looking at the following topics and subtopics. 1. Radioactive decay. Number 2, half-life and decay constant. Number 3, calculations on radioactive decay. Actually, the calculation on radioactive decay will be the subject of discussion in the next video because we are going to spend enough time to deal with that. The objective of our presentation now are: number 1, define and give examples of radioactive decays. Be able to define it and give examples. Number 2, should be able to define half-life and state what half-life actually is. Number 3, we should be able to calculate half-life and decay constant. Like I said, that calculation will be done in video number 3. So now let's go to the next slide for the presentation. Number 1 we're looking at is radioactive decay. What actually is radioactive decay? Radioactive nuclides usually are heavy and unstable. What do you mean if we say they are heavy and they're unstable? They are heavy in the sense that the number of particles you have in the nucleus are very large, very large. And because you have so many protons, I think should be around greater than 82, so many, that repulsion between proton to proton makes the nuclei to be unstable. Because of this instability, the nuclei tend to eject, tend to emit, tend to throw out some particles to become stable. Now look at this nuclide. This nuclide is heavy, is unstable, and it wants to achieve stability. And it does that by breaking down into 2 different elements. The first one and the second one. Although it can also give just a proton or electron, it's also possible. So now they tend to become stable by giving out particles on their own. Remember that word, on their own. Please take note of that. They're giving out particles on their own. That is very important as far as radioactivity is concerned, because these particles are ejected on their own, nothing influencing it, nothing inducing it. Then this ejection, this removal of particles, this breaking up of this heavy unstable nuclei will continue to take place until a stable nuclei will be formed. So that is what we actually refer to as radioactivity. We are going to really spend time to explain some of these things. So now we're now going to go straight, continuing our presentation. So now the next we're going to look at now is the definition of radioactivity. Radioactive decay is a spontaneous nuclear decay or disintegration of a radioactive nuclide. And this disintegration involves emission of radiation in the form of particles, alpha particle and beta particle, and also in the form of radiation, gamma rays, until a stable nuclide is formed. So now look at this definition. Radioactivity or radioactive decay is a spontaneous nuclear decay or disintegration of a radioactive nuclide involving emission of ionizing radiation in the form of particles or gamma rays until a stable nuclide is formed. Now, let's pause a little. What does all these things we are studying, what does this actually mean? Let's try to examine them one by one. What does this actually mean? Let's look at them one by one. We say radioactive decay is what? What is here? It's a spontaneous nuclear decay. Spontaneous means on its own, nothing forces it, nothing induces it. It just break up on its own. It just break down on its own. It just give out some particles and it continue to give those particles out until it becomes stable. That's one thing you need to take note in this definition. Number two thing that you are going to notice in this definition is that we're talking about during this decay, there are emission of radiation and what? Particles. The radiation, the particles are alpha particle, beta particle, and the radiation is a gamma ray. So now these are the things that are removed. These are the things that are ejected from the nuclide to become stable. So now we now move straight to the next subtopic under this. Having analyzed this, we're going to look at number one, alpha particle decay. What does this actually mean? It means that this heavy unstable nuclide we tend to become stable by giving out what? Alpha particles. Let's look at how that will happen. So we have this uranium-235. This element is a heavy and unstable nuclide. Because it's heavy and unstable, it will tend to decay on its own, forming a new element, and then alpha particle will also is ejected. And remember, it's not just a particle giving out. There is also ionizing radiation giving out. So therefore, energy must go along with the equation you are writing. So that gives us the complete equation for the alpha decay. The parent nuclide. The parent nuclide, uranium, this uranium decay to this new element here, and then giving out alpha particle, and energy is given out. Energy is given out. So that's the alpha decay. Now, having explained what we mean by alpha decay, we are now going to go further to illustrate that. But before then, please like this video and share the link of this video with others. So now, we're now going to look at example of that. Now look at the same element again. What happened again? Goes another decay, radioactive decay, producing a new element. And this new element also emits alpha particle, and energy is also released. So energy is also released. So it's very important. Energy is always released. This decay process continues until a stable nuclide is formed. That's what we refer to as radioactive decay or radioactivity. So now, we're now going to look at radioactive decay. The number one we'll look at is alpha particle decay. Now let's watch the animation. That is writing the equation, the chemical equation. Let's look at that. This is what I told you. This is what I told you before, that this element we are looking at now is heavy and unstable. And because it is heavy and unstable, remember I told you it's going to do what? Undergo what? Decay. Can you see it? It's excited. Now, that excitation means this parent nuclide, this unstable parent nuclide is going to remove some particles. What happened? It ejects alpha particle. That's alpha particle decay. And then the daughter nuclide is another element that is formed. What do you notice here? After the decay, the nucleon number of the daughter nuclei decreases by 4, while the proton number of the daughter nuclei decreases by 2. And that amounts to the particle given out. Remember, there is energy also radiated. Very important, you should note that there's energy also radiated. This is what is referred to as alpha decay. So you can see the equation of that alpha decay. Remember, in every chemical equation we write, energy must go along with it. Very important, the energy must go along with it. Now this is a specific example as we already seen in the other slide. So now, we are seeing alpha particle decay. Now, what are the characteristics of alpha particle decay? You can see from this animation. Number one, alpha particle decay produces what? A new element. What is the new element produced here? That is this, the daughter nuclei, different from the parent nuclei. That's a new element produced. Another element produced here is the alpha particle that we are referring to. That's another new element produced. So therefore, this will always lead to what? Production of new element. The number two, the new element formed is shifted 2 places or displaced 2 places to the left of the original element in the periodic table. What do we mean by that? Look at this also. Do you see this? The proton number is 92. Look at it very well. What is the proton number of the daughter nuclei formed? 90. So it's shifted 2 places to the left in the periodic table. So the basic thing here is that a new element is formed, and the position of that element is 2 places to the left of the parent nuclide. So very important, you should take note of this and write them down in your jotter. The number 3, the proton number of the element produced decreases by 2. Of course, we have mentioned that before. Look at this decay. The proton number here is 92. The proton number here is 92, but the daughter nuclei is now 90. So there is a decrease by 2. 90 minus 92 will give us a 2. So there is a decrease by 2. So that's what we are saying. So you have the decrease by 2. And then finally you have the nucleon number also decreased by what? 4. We mentioned it. Look at this. This is 234 and this is 230. So now the daughter nuclide, the nucleon number is 4 less than the parent nuclide. So therefore, the nucleon number decreased by 4. So now that's what happens during alpha particle decay. So now we are going to go to the next one, radioactive decay. Number 2 we are going to be looking at is beta particle decay. Now, look at it again. You can see it clearly here. This element you are seeing here, can you see this element? Is what? Heavy and unstable. And it's excited. Because it's heavy and it's stable and it's excited, it's going to do what? Decay by giving out particles. But in this case now, it's going to decay to give out a particle that's less in mass to the alpha particle. So you have unstable parent nuclide decays by emitting alpha particle or electron. Sorry, beta particle or electron. So let's watch the animation. Do you see what happened here? It decays by giving out alpha particle, and this is a new element that is formed after the alpha particle is given out. So here, this is the daughter nuclei and this is the parent nuclei. So without wasting time, what are the characteristics you notice from here, like we did in the alpha particle decay? But before then, please subscribe. What do you notice here? This is the chemical equation. The proton number of the daughter nuclei increased by 1 because the charge of electrons is -1. That leads to an increase in the mass of the daughter nuclide. Then electron or alpha particle is produced, and also large amount of energy is released. So now we have seen that this is a specific example of beta particle decay. You have here sodium decay to magnesium, and then ejecting electron or beta particle, and energy. So now, what are the characteristics of this? Number one, you see that a new element is produced. You can see those two new elements. You see this one here, see this one here. Let me just circle them. So this is the first element produced, and this tiny beta particle is another element produced. So new elements are produced. So new elements are produced during beta particle decay. Now, what happens to those new elements? Like I said, look at this equation here. The nucleon number remained unchanged, but the proton number increased by 1. So you can see clearly the sodium 2411 decay becomes a magnesium 2412. There's an increase in the proton number, and the new element magnesium, no more sodium, is formed. The number 3 you see here is that the new element formed is shifted or displaced one place to the right. Remember when it decreases to the left, now that it's increased, it is to the right in the periodic table. That's what happens during beta decay or decay by emission of electron. So now we're going to look at the next one, decay by neutron or neutron particle decay. Once again, you see this, it's heavy and it's unstable. So that's the parent nuclide. Now, the parent nuclide, heavy and unstable, and because it's heavy and unstable, it becomes excited, having a lot of energy, and that energy will lead it to decay. It gives us a neutron, and then forming a new element, the daughter nuclide. And remember, that's the daughter nuclide. Then this is the parent nuclide, the original element before this decay. So now what do you notice here? What do you notice here? Look at here, Z remains the same, no change in Z. But the nucleon number increased by 1 because proton has mass but no charge, right? Neutron, has no mass but has no charge but has a mass of 1. So therefore, the nucleon number increased by mass 1, the proton number remains unchanged. So now, decay by emission of gamma rays. So you can look at the characteristics. I don't need to be writing everything. We don't have much space to write. So you can look at it. A new element is formed, and the nucleon number increased by 1. And because the nucleon number, there's no change in the proton number. There's no displacement, there's no change, there's no shift in the position of the element formed in the periodic table. A new element actually is not formed. It's an isotope that is formed. So now we have the next one, emission by gamma emission. In this case, the decay by gamma emission. Remember what we said in video 1. Gamma is an electromagnetic radiation. It's an electromagnetic radiation. And all electromagnetic radiations are waves. And because they are waves, they do not have a mass. They only have energy. Just like this. They have energy, no mass. And because they have energy, the energy of the parent nuclei will decrease after this decay. So now let's see what is going to happen. Now, you have the parent nuclei, and that parent nuclei is heavy and unstable. And because it's heavy and unstable, what is going to happen? You see that? This is what happened. It emits radiation. There's no change in the nucleon number. There's no change in the proton number. So no new element is formed. No new element is formed. So beta decay produces no new element. What happened? There is a change in the state of energy. Before the decay, the nucleus has a lot of energy. After the decay, the nucleus loses certain amount of energy and becomes less excited. So now, but remember, no new element is formed. Then we'll now come to the next concept we want to look at, half-life. Now, what do you mean by half-life? The half-life of a radioactive element is the time it takes for half of the original number of atoms or mass of that nuclide, of that sample of a nuclide, to decay. That time it takes half of that amount to decay is what we refer to as half-life. That's why I say half-life is the time it takes half of the original number of atoms or nuclide in a given sample of radioactive substance to do what? Decay. If you have 2,000 particles and in 30 seconds it reduces to 1,000, so the half-life is 30 seconds. If you have 10,000 particles and in 50 years it reduces from 10,000 to 5,000, that means the half-life is what? The half-life is 50 years. So that's what we refer to as half-life. Usually we represent that with small t or capital T. Let's watch this animation to actually illustrate that. Then you have these particles here. Then I have my watch. Then I will start the counting. Now, what happened? There's the hand of the clock is moving. There's decay taking place. Now, what happened now? It has decayed up to half. So now, you see that the half-life is 5 seconds. It took 5 seconds for half of this element to decay. So therefore, the half-life is 5 seconds. So now, stable elements have long life. What do you mean by stable element? The element that exists naturally in nature, like oxygen, chlorine, helium, name them, iron, chlorine, magnesium, gold, lead, name as many elements as you can remember. All of them are stable because they have very long half-life, sometimes in billions of years, billions and millions of years. Therefore, they are usually stable. So, because of that, they do not disintegrate on their own spontaneously. They do not disintegrate spontaneously. They do not undergo decay on their own. You have to force it. You have to induce it because they are stable. So they must be induced in order to disintegrate or decay. So now we have seen that. Now you see that this nucleus is heavy and it's unstable. So if it's stable, it will not decay. But if it's unstable, it can decay on its own. Unstable elements or radioactive substances have short life. Now, radioactive elements, radioactive sources, radioactive materials have short half-life. Some of them, their half-life is so short that they cannot even exist in nature in fractions of seconds. Some of them in minutes, you may not find them if you bring them out from wherever you are mining them. By the time you expose them, they will transform to other elements. So they keep disintegrating until a stable nuclide, a stable substance is formed. So that is a radioactive materials and the half-life. So when the half-life is long, you have stable materials, stable elements. And when the half-life is short, you have unstable elements. So now, we have seen that what we mean by half-life and how it relates to stability of elements. When a radioactive substance decays, take note of that. When a radioactive substance, when they decay, the rate of decay is what? Proportional. Of course, you should know that. If you have 20 billion particles, so the rate of decay will be faster than when you have only 5 particles. So therefore, the rate of decay is proportional to the number of atoms at the beginning. More particles, the faster they decay. Less particles, the less they decay. The rate of decay will be slow, will be small. So therefore, the more atoms in the beginning, the faster they decay. Please, that's very important. You should know that. That's why we say the rate of decay. The rate of decay. If I write the question, the rate of decay, the number of atoms at the beginning with respect to time is directly proportional to what? To the number of atoms at the beginning. N0 is the number of atoms at the beginning. The rate of decay is directly proportional to the number of atoms at the beginning. So now, you see that unstable nuclide here. If you allow it, if you expose it, it will just undergo decay on its own. So therefore, the equation I wrote before said the rate of decay is what? Directly proportional to the number of atoms at the beginning. I've written the equation already, I've seen the equation. Then we move to the slide for the final discussion. And we'll be looking at the decay curve. The decay curve. Now, how would the decay curve look like? This is the number, remember what I said, this is the number of atoms at the beginning. And that's what I represented in that equation as what? N0. I represented that in that equation as what? N0. So capital N0. So that's what it's supposed to have here, capital N0. So now that we have that, we want to see what is going to happen as the atom decay as we saw in that animation. Now, at the beginning, you have full number of atoms. Let's see what is going to happen. So now you have this. That's how the curve will look like. Now let's watch. You have here the number of atoms. How many do you have here? Count it. 8 particles. Now that's what you have at the beginning. So the number of atoms at the beginning here is what? 8 particles, as I said here. Now let's see what is going to happen. After half-life, that's T-half. After this T-half, the half-life here, what happened? The number of atoms dropped from N0 to what? N0 divided by 2. That's half N0. Half of it have decayed. Half remained. So now, at the beginning, you have 8 particles. Now we're having how many here? 4. Now, another half-life. Let's see what is going to happen. So here you have half of the atoms remains after the first half-life. Half remain, means half have what? Decayed. Now, let's see what is going to happen. Another half-life. The number of atoms drop now from N/2 to N/4. Half of N/2 have decayed. That's the second half-life. The number of particles now shifted from 2 to what? 3. Now, you have the number of atoms like that. And remember, this curve will never intersect, will never cross the time axis, or else the atom or the element will disappear. And that is not possible. So that will not happen. So whenever you are drawing the decay curve, it must not touch the time axis, but it must touch the vertical axis, representing the number of atoms at the beginning. Please, we have come to the end of this presentation. Please subscribe, like this video, share this video, and click for alerts so that when the next video is released, you will be notified. Thank you for studying with me.